In this video, I want to review lecture slides related to sampling techniques. So here is a Markov chain. We have this famous grasshopper jumping here and there, and you see it states it's moving from 0 to +1 with 0.25 probability, and 0 to -1 with 0.25 probability. So and so on. So those arcs are basically different states. Uh, one one thing that is really important to kind of remember or keep in mind, even though this example is just a one state, one dimensional, this applies to n dimensional. Meaning, for example, when we talk about state of a system, it doesn't necessarily mean one dimensional state. So for example, like in this example, so see we have this system with um, various variables, the D, I, G, S, and L. So if you take a snapshot of this, for example, like D0, I0, G0, and some values for L and S, so these different snapshots, that is a state. Each snapshot is a state. So I want to make sure that we don't have this in mind, that this state transition is one dimensional, which is quite obvious, obviously, if you know this stuff very well, which is why these X's are in bold letters. Um, so so basically you have this chain where it is jumping from one state to other state and so on and so forth. And this T is the transition model from current state X to a new state X prime. And for all X, the moving from X to X prime, they all sum to 1. So the other way of reading this sigma all over X prime, the new states from current to new states, is like a transition matrix. But here in this slide it's given as a summation. The next thing is stationary distribution, right? We saw the grasshopper jumping from T0 to T1, T1 to T2, and so on and so forth. Now, if probability of the probability at time step t of x prime, which is the new state, is approximately equal to probability at time step t plus 1 of x prime. That's when stationary distribution is reached. Meaning over a long, so if you let the grasshopper or a given system keep jumping from one state to other state over a long period of time, they will have this. So if we reach this condition that p of p at time step t of x prime is equal to p at t plus 1 of x prime, then we say stationary distribution is reached. Now, see, note this p superscript of t, brackets begin x prime, brackets close. See how she maps that to pi of x prime. That's what that pi of x prime is. So in case sometimes it can, at least the first time I saw pi reminds me of 22 by 7 or some product, but anyway, so that's the notation. Pi of x prime really is that p of at time step t of x prime is equal to p at t plus 1, which is, how is that arrived? Using the transition matrix or this transition model. You multiply the current pi of x with the transition model, and you sum over all x. That's how you get this station. That's how you get this right hand side part of the equation. So when p of x prime, which is the new state, is equal to pi x of the transition from x to x prime. Now you can view this, so without this sigma notation, that pi is a row vector and t is, you can view pi as like a row vector and t as a transition matrix, and you multiply them, you get this sigma notation. So But here basically they're saying for all x, you take pi of x, and then multiply that with the transition from x to all possible outgoing x prime states. And that's what is explained here. The next thing is, okay, we have a stationary, okay. So Gibbs chain, right? So we talked about in the last two slides about the chains, right? How they're moving from one state to other state, how they've reached a stationary distribution. But so how in the first place can we get a Markov chain, right? So so we have some system, but how in the world are we going to generate this chain, this Markov chain? So that's where this Gibbs sampling and Metropolis Hastings algorithms will come into play to generate this Markov chain, right? So that's the whole point of this. We are trying to generate that Markov chain. That's why you have this Gibbs chain and this Metropolis, and also you can use Metropolis Hastings algorithm to generate these Markov chains. So in Gibbs chain, so just as explained, now there are some beautiful tutorials by my fellow TAs on the forum. Also in the rewritten version of the document, there is a nice flowchart. So if this is slightly confusing, I would highly recommend go and just take a look at that. So if I have n variables, x1 through xn, right? For example, in this example, x1, x2, x3, you take one variable at a time. So for each variable, you take one variable at a time. Like for example, you take x1, give it equals 0, x3 equals 0. You sample that, and let's say we get 1, 0, 0. And then the next thing you do is you go to the next variable x2, probably of x2, given x1 equals 1, x3 equals 0, and then you do the one variable at a time. So you do again the final variable. Let's say you take probability of x3, x2 equals 0, and then let's say in the end we get this 1, 0, 1. So, and then that's our state for this one iteration, and then you set x prime equals this x, and then that's how the Gibbs transition model works. So you sample one variable at a time. Actually, I'll talk a little bit more when we do this Gibbs trans and block log distribution example in the assignment. So one variable at a time. The problem with Gibbs chain is because you're sampling, you're taking only one variable at a time, it can be slow. So that's the thing with one of the problems with Gibbs sampling is it can be slow since it only updates one variable at a time. Also, if the variables are highly correlated, then it will take a long time to mix or reach the stationary distribution. So here is the same, here is just another example. I'll not go in detail, but yeah, it's the same thing. The most important, when we talk about state, it is the snapshots at different times where these things can different values and so on. So the next slide is, so then in the lecture, we have the professor talking about reversible chains, which will be a key concept in the Metropolis Hastings algorithm. So here is your distribution. Now, we keep talking about distribution. So what is this distribution? Distribution is something where you basically go and take a look up. It's just like a normal distribution or something like that. So basically, you get values out of it, right? You can go probability of x equals something, you go and look into it, and you take the value, and the distribution is arrived through some function or some way. So in a reversible chain, pi of x times the transition model, that is moving from x to x prime, is equal to pi of x prime, which is the new state, times x prime to x prime. So that is going from here to here. So if you multiply pi of x with the transition model, that will be equal, that will hold good in the reverse direction, which is pi of x prime times t of x prime to x. Now using this, we can write this as our new state. I mean, you can follow this derivation right here, but basically in the end, this is the detailed balance equation, which is pi of x prime is equal to the new state, right? The pi of x prime is the new state, is equal to the current state times the transition multiplied by the transition model. So that's the most important thing. That's what this detailed balance equation is. So in Metropolis Hastings algorithm or Hastings chain, you have two things, which is the proposal distribution q of x to x prime, given x, what is the proposal distribution to go to x prime. Again, when we talk about distribution, you can imagine this as some, let's say you have a lookup table for some probability and of x going from x to x prime. You're looking up and getting a value. That's what that you're getting those values from the probability distribution table. That's what the distribution is, really. Acceptance, now again, how the distribution in a different scenario. For example, how you can have a uniform distribution on how it goes from x to x prime, or some other or block log distribution, which you will see in the assignment, so on and so forth. Acceptance probability is again same thing, probability of accepting the proposal from of going from current state x to x prime. Obviously, the transition model would be a product of your proposal distribution and acceptance distribution. That's how the transition model would be defined in this case, right? So that's what so that's the q times a. That's the transition model in Metropolis Hastings chains. So yeah, so using that q times a, so that's basically going back to using the detailed balance equation, pi of x times t of x to x prime is equal to pi of x prime times t of you can then substitute, take this t out and use the q times a that we just discussed before, and then eventually you will get this most important equation, which is the acceptance probability. A of x to x prime equals a of x to x prime divided by a of x prime to x, and pi x prime times q x prime to x divided by pi of x prime. So the most important equation you will keep seeing everywhere in the programming assignments, and this is very important to understand. And basically the acceptance probability is given by minimum of 1 comma this numerator value by this denominator value. So I'll stop here because I can't make very long videos. I can only upload videos up to 15